Hello, my name is Paul Geyer, and I will be talking to you today about roofing systems. These are the chapters in the book, so to speak, how I will be dividing up the information or presenting it. Starting points for roofing system selection considerations for steep roofing systems, for low slope roofing, re-roofing and recovering, environmental issues, some information on details, using principal design considerations to reduce the number of possible roof systems, considerations when specifying low slope membrane roofing, principal considerations when specifying steep slope roofing, and additional criteria and discussion. By way of introduction, this is a little bit about me and what I've been doing for the last few decades. For 35 years, I was what I characterize as a straight-ahead designer, cranking out drawings and specifications for buildings and related infrastructure. I got registered in a few things along the way. And for an additional 9 years after that, I was in the public policy area as a principal staff advisor to the California legislature on capital outlay and infrastructure issues. This discussion is intended to introduce the major considerations in selecting a roofing system. Figure 1, which you will see in a moment, depicts the various alternative roofing systems and how they relate. When commencing the selection process, there are two different starting points. Figure 1 indicates the decision process for arriving at the best roofing solution for your building. There can be an issue, of course, whether you're talking about new roofing or re-roofing. The roof may be part of a new building design, or it may involve the re-roofing of an existing structure, either replacement or recovering. Today, approximately 75% of roofing activity is re-roofing. In new construction, the designer is very likely to have a preconceived notion as to whether a highly visible sloped roof is wanted or whether a less visible low slope roof design is acceptable. Positive drainage is a very important design criterion. When re-roofing, it may be feasible to improve drainage by using tapered insulation or sloped deck fills. Table 1 evaluates common steep roofing systems based upon some use criteria. Steep roof systems make a strong visible statement about a building. The texture, shadow line, and color are major factors in selection. Steep roofs function by shedding water rather than by being waterproof. Figure 2. Minimum slopes, as shown in Table 13, are required in order to ensure proper drainage. Major categories of steep roofing include asphalt shingles, wood shingles and shakes, tile, slate, architectural metal, asphalt roll roofing, and fabricated units of metal or plastic intended to look like the others. Only asphalt roll roofing and asphalt or wood shingles may be recovered. Sloped roofs are effective snow shedders. In addition, the attic space that accompanies steep roofing makes it easy to ventilate the roofing system. Figure 2 indicates a typical steep roofing system, sometimes characterized as hydrokinetic. Figure 2 indicates a low slope roofing system, commonly or sometimes characterized as hydrostatic. Sloped roofs in general require less maintenance than flat roofing systems. When considering re-roofing a flat roof, it may be possible to convert the low slope roofing system to a steeply sloped roof. This may improve the appearance of the building while resolving drainage problems as well. Steep roof conversions are a viable option for relatively narrow buildings. Table 1 indicates steep slope selection possibilities based upon use criteria. The types of roofing covered include asphalt shingles, asphalt roll roofing, clay tile, and concrete tile. Membrane roofing is typically used on commercial buildings where the minimum slopes required by steep roofing render them impractical for larger buildings. Low slope membrane systems are completely sealed at laps and flashings, figure 3, and can temporarily resist standing water conditions. Choices for membrane roofing include multiply bituminous built-up, abbreviated sometimes BUR, polymer modified bituminous, MB, elastomeric single-ply systems, EPDM, thermoplastic single-ply systems, PVC or TPO, sprayed in place polyurethane foam, SPF, and some metal, hydrostatic low slope SSSMR systems. Designers frequently select low slope roofs when the roof is expected to accommodate rooftop equipment. With the exception of foam and metal, all low slope systems can be incorporated into protected membrane roof designs. The term replacement is used when the existing roofing system is to be either partially or totally removed and a new system installed. The designer should consider any existing problems and whether drainage and thermal performance needs to be improved. Existing surfaces such as walls and curbs may be contaminated with bitumen, which might affect compatibility with some re-roofing options. Additional concerns as compared to new roofing include whether the existing structure can handle a significantly heavier roof system and whether construction activities of the re-roof system will affect the occupants of the building, such as fumes, falling debris, and noise. The term recover is used when a new roofing system is to be superimposed directly over an existing system. In this case, underlying conditions are obscured, making assessment of their condition more difficult. Additional concerns include how the recover system will be attached to the existing membrane or roof deck and compatibility with the substrate. The potential for trapped water between the old and new membrane may suggest the use of venting base sheets and/or roof vents. A relatively new design criterion is whether the roof system under construction meets green criteria, such as whether the system incorporates post-consumer waste or is itself recyclable at the end of its useful life. Roof system waste is bulky and puts a great strain on waste disposal sites. Energy efficiency is also important in terms of raw materials acquired, production of finished goods, and application of the roof system. Thermal performance in service and retention of thermal value with age are equally important. A sustainable or robust roof is highly desirable as extension of the life of the roof contributes to overall conservation. High albedo, that is, reflective roofs, may improve localized climate conditions. The felt used in asphalt organic shingles consists primarily of recycled waste paper, wood chips, and sawdust. Asphalt itself is a byproduct of petroleum refining. Wood fiber and perlite roof insulation contain waste paper. Glass fiber and asphalt organic shingles have been recycled into asphalt curbing and the like. Wood shingles and shakes can be recycled into garden mulch. Steel and aluminum contain recycled scrap, and at the end of their life, metal panels can be recycled back into scrap. Tables 2 and 3 compare environmental considerations for steep and low slope roofing systems. Table 2 provides a comparison of environmental issues for different types of steep roofing systems. And Table 3 provides a comparison of a variety of low slope roofing systems and environmental issues of concern. Once a tentative roofing system selection has been made using information provided by this discussion, detailed information is developed. Tables 4 and 5 list some of the principal design considerations in roof system selection. An explanation of the headings follows the tables. These tables are not all-inclusive but contain many criteria that the designer can consider to reduce the myriad of choices. Systems that fail to meet the principal project design criteria can be quickly disqualified from further consideration. For example, if an existing structure has reached its design load limit, then heavier roofs, such as ballasted single-ply roofs or concrete tiles, would have to be disqualified, or the structure would have to be strengthened at significant cost. Table 4 provides qualitative guidance for principal design considerations for steep roofing. Considerations of initial cost, lowest life cycle cost, construction difficulty, inspection and repair difficulty, and estimated life years. Also suitability for cold and hot weather, resistance to wind and hail, traffic resistance, and chemical resistance. Table 5 provides qualitative guidance for principal design considerations for low slope roofing. The initial costs, life cycle costs, construction difficulty, inspection and repair life years, suitability for hot and cold weather, resistance to wind and hail, ponding, traffic resistance, and chemical resistance. The initial cost may include materials, labor, and special setup for construction. Initial cost may determine if the roof, as designed, is affordable. Perhaps a somewhat less expensive system should be considered if it does not incur significantly increased maintenance cost or have a shortened life. Life cycle cost considers durability, but also presumes that routine maintenance will be performed to achieve the projected life. Consider whether the building is temporary or permanent. It would be hard to justify an expensive copper or slate roof on a building scheduled for demolition in the near future. Also consider the mission of the building. There are levels of quality in many systems. For example, while 45 mil EPDM is the standard, for little extra cost, 90 mil material with greater puncture resistance or conversion to a PMR system could be specified for a building with a critical mission. Some systems require more clearance to accommodate application methods and equipment. Large prefabricated roof sheets, 50 feet by 200 feet, may be fine on a large roof with few penetrations, but are impractical on a roof area that is broken up by many curbs and equipment supports. On multiple penetration surfaces, relatively narrow sheets, i.e. BUR, MB, thermoplastic, single ply, or sprayed in place polyurethane foam should be considered. Penetrations through standing seam metal roofing need to accommodate the expected thermal movement of the metal panels. Thermal movement is cumulative, increasing with distance from the point where the panels are restrained, which is typically the eaves. Penetrations in SSS-MR panels must pass through the flat portion of the panel, not through the standing seam. Penetrations wider than a single panel require a diverter to carry water around the obstruction. Water must flow parallel to the raised seams, never over them. Some roof systems require periodic recoating for weather protection. Aggregate surfaced roofs are more difficult to inspect and patch than smooth surfaced roofs. A mean life is listed, but the actual life is affected by drainage maintenance and extreme use or abuse. The effects of freeze-thaw, hail, ice scrubbing, and traffic while cold, that is snow removal typically, is considered. Some materials embrittle dramatically at low temperatures, that is, they have a relatively high glass transition temperature. Others may embrittle as they weather and lose plasticizer or are degraded by ultraviolet or thermal loads. H indicates highly suitable, L indicates less suitable. Effects of thermal expansion and algae growth are considered in the suitability in extremely hot or humid conditions ratings, H indicating suitable and L indicating less suitable. With regard to wind resistance, roofs are vulnerable to wind scour and blow off. While arbitrary ratings are provided in the tables, the resistance is affected by building height, terrain, parapet height, and measures taken to upgrade perimeter and corner attachment. 8H in the tables indicates highly wind resistance when properly designed. For membrane roofing, impermeable roof decks such as cast-in-place concrete are best. Air retarders are needed with loose-laid and mechanically fastened single-ply systems, as they may otherwise balloon from interior air leakage. Perimeter wood blocking must be well anchored to prevent peeling of the membrane or loss of fascia metal. Avoid the use of small aggregate, i.e. pea gravel, near tarmacs and on skyscrapers due to the damage it can cause if blown off the roof by high wind. Asphalt shingles may require manual application of tab adhesive. Interlocking asphalt shingles provide excellent wind resistance. Metal panel systems are wind resistant only when all components include clips, fasteners, and secondary structural members are installed as wind tested. SPF has outstanding resistance to wind and to wind-blown missiles. SPF roofs performed well in Hurricane Andrew, especially when they were spray applied directly to concrete roof decks. Membrane roof systems rely upon sealed seams to resist hydrostatic pressure. Water absorption may result in root or algae growth or cause rot. In the tables, H refers to highly resistant to these conditions systems. Roofs that have a lot of rooftop equipment will have foot traffic that can cause punctures or abrasion. Most roof systems are available with traffic protective overlays such as walkways. In the tables, H indicates highly resistant systems to abuse, assuming protective courses have been applied. With regard to resistance to chemicals, including oils, fats, grease, and metal ions, some roof surfaces are vulnerable to exhaust fumes or liquids. Thermoplastic polyoleifines, TPOs, and hypalons, CSPE, may be better than bituminous materials in resistance to oils, greases, and solvents. Copper containing runoff water from condensate coils or flashings will corrode zinc and zinc aluminum SSS-MR roofing. In the tables, H indicates better than average resistance to attack. Consider the total number of roofs already installed, the weight of the proposed roof system possible, and construction loads. The unit weight of membrane systems vary dramatically, ranging from less than 0.5 pounds per square foot for a 2-inch thick of SPF roofing to more than 20 pounds per square foot for ballasted single-ply systems. Typical roof system weights and construction loads are shown in Table 6. Roofing systems are rated as entire systems, including the roof deck, method of attachment to the deck, such as fasteners, hot bitumen, cold adhesives, vapor retarder if used, thermal insulation, roof membrane, and surfacing. Typical external fire ratings, ASTM E108 classes A, B, or C, are shown in Tables 7 and 8. Combustible decks, wood, plywood, OSB, oriented strand board, require selected combinations of underlayments, insulation, roof, and surfacing to resist burning brands and intermittent flame, as described in ASTM E108. Principal roof decks for membrane roofing include steel, cast-in-place concrete, precast concrete, wood, plywood, oriented strand board, and structural wood fiber. Variations of cast-in-place concrete include lightweight structural concrete, typically 105 pounds per square foot, and lightweight insulating concrete, typically 30 pounds per square foot. In new design, the roof deck is generally selected based upon construction considerations and materials. Steel is by far the most popular, followed by concrete and plywood OSB. Table 9 lists some criteria for deck selection for new construction. Table 9 lists methods of attachment to the roof deck. Attachment options include full adhesion, mechanical fastening, and loose-laid ballasted roofing. Steel decking requires a bridging course, typically mechanically fastened roof insulation. For steel roofing, plywood and roof decks are most common. They generally utilize flexible batts as underdeck roof insulation, although architectural metal and cathedral ceiling constructions may use rigid insulation above the deck. Table 10 lists some possible combinations of suitability of the membrane for the substrate. Table 6 indicates typical weights of roofing materials and equipment. Table 7 indicates fire ratings and required underlayments for steel-sloped roof systems. The roofing systems indicated in the first column, the ASTM E108 class indicated in the center column, and the underlayment indicated in the column on the right. Table 8 provides fire ratings and required underlayments for low-slope roof systems. The roofing systems are indicated in the first column on the left, the ASTM E108 ratings in the second column for combustible decks, and in the third column from the left for non-combustible decks, and then the construction of the deck indicated in the column on the right. Table 9 indicates the suitability of roof decks for various conditions. The various conditions are economy, long spans, resistance to heavy roof traffic, seismic, internal fire resistance, external fire resistance, wind resistance. The roof decks considered are indicated in the first column on the left, and the qualitative ratings range from excellent down to poor. Table 10 indicates membrane substrate compatibility and attachment methods. Rigid thermal insulations used under membrane roofing include wood fiber, perlite fiber, glass fiber, foamed glass, polystyrene, either extruded or expanded, and polyisocyanurate isoboards. Non-structural thermal insulations include glass fiber and mineral wool batts, blown loose insulations such as cellulose fiber, glass fiber, mineral fiber, and expanded vermiculite. Table 11 indicates suitability of rigid roof insulations for membrane roofing based upon intended method of use. Table 11 indicates the suitability of roof insulations for the method of use. If thick layers of insulation are needed to meet a high therm resistance, thicker wood nailers and deeper fascia metal will be required. Foam plastics such as polyisocyanurate and polystyrene have the highest R values per unit thickness. In standing seam metal roof systems, the permissible thickness of blanket insulation may be limited by the clearance provided by the supporting clip design. Blanket insulation used in steep roofing systems is frequently placed on the floor of the attic, where R values of 30 or more may be possible. Refer to Figure 13. Drop ceilings are sometimes insulated by placing batts directly above the ceiling panels. This practice is not recommended as subsequent access to underdeck equipment or phone wires is blocked. When the insulation is displaced to gain access, it is rarely put back in place correctly, if at all. With regard to suitability for extreme climates, protected membrane systems, PMRs, are very well suited to extremely cold climates and have been successfully used in all climates. For extreme conditions of snow and ice, a cold, ventilated roof should be considered. For most steep roofing, this is achieved by allowing a flow of outdoor air between the insulation and the roofing deck. This air cools the roof in summer, dries out any moisture that condenses in the roof, and greatly reduces the formation of icicles and ice dams along the eaves. For regions prone to severe hail, ballasted EPDM roofs are very good and PMRs are excellent. Tile, shingles, and bare BUR and metal systems are easily damaged by hail. In regions of semi-tropical climate, high temperatures and humidity, asphalt shingles should be treated to be fungus resistant, and wood shakes and shingles should be pressure treated for rot resistance. Most membrane systems are difficult to install in sub-freezing weather. If frequent precipitation during construction is a problem, factory fabricated single-ply systems with field-welded seams may have advantages over systems where field application of adhesives or hot bitumen is needed. Torch-applied modified bitumens are one of the few systems that can be applied, albeit slowly, in wet, windy conditions. The NRCA Commercial Low-Slope Roofing Materials Guide contains a comprehensive side-by-side comparison of commercial roof warranties. The roofing industry offers two general types of warranties: materials only and materials and workmanship. Carefully read the exclusions and limits. Note the longest warranties are not necessarily the best, nor does the length of the warranty directly relate to roof durability. In many cases, manufacturers may restrict their warranties. Sloped roofs require less routine maintenance and may be preferred when the facility management is incapable of providing routine inspections and minor repairs. Modified bituminous and BUR systems may be superior in abuse resistance to thin single-ply systems. Various protection boards walkways can be used around equipment where traffic is anticipated. Protected membrane roof systems are abuse resistant but more difficult to inspect and repair. There may be issues of roof access, fumes, and property protection when re-roofing. With regard to fumes in re-roofing situations, fumes from kettles and solvents may be objectionable. Hot coal tar pitch is especially objectionable. Hot asphalt is also noticeable but less noxious. Cold applied systems with taped or welded seams and metal roof systems generate few odors. It may be necessary to coordinate air conditioning shutdown to avoid taking fumes into the occupied building. If the area around the construction site is congested, it may make heating and hoisting of roofing materials difficult. Site access, material storage area, layout area, building, and landscape protection should be identified on drawings. The presence of occupants, vehicles, and pedestrians may be of concern. Re-roofing is noisy. Dust and overspray may affect those nearby. Roofing requires skilled installers. Qualified contractors and inspectors are more likely to be available if the system is customarily used in the region. It should be determined whether there are several manufacturer-approved installers capable of bidding the work. Verify that the contemplated system is acceptable to the owner, occupants, and maintenance personnel. With the exception of SSSMR, membrane roofing requires a suitable roof deck. Most constructions will also use thermal insulation. Vapor retarders are sometimes required to protect the roofing system from attack by moisture from the interior. Built-up roofing BUR systems consist of multiple reinforcements such as asphalt-treated glass or organic felt laminated together with hot-applied bitumen, asphalt or coal tar pitch, or cold adhesives. See Figure 4. Surfacings include aggregate coatings, cap sheets, and sprayed roofing granules. A typical system includes thermal insulation and may include a vapor retarder. Figure 4 indicates a typical built-up roofing system consisting of the structural deck, vapor retarder, thermal insulation, base layer, top layer, the felts and the bitumen, and then the aggregate on top. MB, polymer modified bitumen, consists of reinforced sheets factory coated with polymer modified bitumen. They may be laminated in the field using hot bitumen, heat fusion, or by cold adhesives. Refer to Figure 5. Surfaces include cap sheets with mineral granules, metal foil, and field-applied coatings. Figure 5 indicates a typical polymer-modified cap sheet adhered to mechanically fastened base sheet. Elastomeric single-ply membranes consist of a factory-produced sheet, generally of EPDM rubber with seams field sealed with adhesive or tape. Refer to Figure 6. Sheets are unsurfaced unless ballast is used. Elastomers are vulcanized, thermoset, and usually non-reinforced except when used in mechanically fastened systems. A fleece-backed sheet is also available for fully adhered systems when it is desired to use hot bitumen as an adhesive, for example, for recovering an asphalt-contaminated deck or old built-up roofing system, BUR. Figure 6 indicates a typical EPDM roof system. Figure 7 indicates a typical PVC roof system. Weldable thermoplastic membranes consist of a sheet of reinforced thermoplastic material such as PVC or TPO. Sheets are unsurfaced or ballasted. Seams are generally heat fused, although solvent welding and adhesive bonding are also possible. Refer to Figure 7. Structural standing seam metal roofing, SSSMR, consists of metal panels with raised seams more than 1.5 inch high. Refer to Figure 8. Sealants are utilized at side seams and end laps to provide waterproofing. Most are considered hydrostatic, resisting standing snow and occasional ponding. A word of caution: ridges and valleys of structural standing seam metal roofing may not be as watertight as the seams. Figure 8 indicates typical structural standing seam metal roofing systems. SPF, sprayed-in-place polyurethane foam systems, is a thermoset rigid foam field formed by the reaction of liquid components in the presence of a foaming agent sprayed onto the substrate. SPF is protected by liquid applied elastomeric coatings or an application of loose gravel on slopes less than 4%. Figure 9 indicates the typical elements and components of membrane roofing systems. The components of membrane roofing systems: first, the deck, which supports the roofing loads and is selected to conform to fire-resistant design classifications. Not all systems require a deck, for instance, structural standing seam metal roofing. A vapor retarder protects the insulation against moisture vapor attack from the warm, high vapor pressure side of the roof assembly. Not all buildings require a vapor retarder. An air barrier prevents air movement, infiltration, and exfiltration through the roofing system. Thermal insulation provides thermal resistance and prevents condensation on components beneath the insulation. It also furnishes support in a smooth, continuous substrate for the membrane. The membrane is intended to keep water out of the components below as well as out of the building. The membrane system affects fire resistance. Individual roofing components may be held in place by adhesives, fasteners, ballast, or a combination of these methods. Perimeter flashings are waterproof vertical terminations of the membrane. Refer to Figure 10. And Figure 10 indicates representative wall base and cap flashing. Roof edging and fascia are usually low profile roof edge terminations and side trim. Roof penetrations include drains, vents, curbs, equipment supports, and the like. Surfacing materials screen UV light, improve fire ratings, and may improve water and/or hail resistance. With regard to attachment for low-slope roof systems, first, full anchorage. For relatively inelastic roof membranes such as BUR and MB, solid adhesion helps restrain the roof membrane and uniformly distribute thermal stresses. When insulation is used, it is fastened or adhered to the deck. The membrane is fully adhered to the thermal insulation using hot asphalt or cold adhesive. Polyurethane foam is sprayed directly to the substrate, especially in recover of existing BUR, thereby being fully adhered as well. In partially attached systems, the membrane is mechanically anchored through the insulation into the deck, or in a few cases, partially adhered with strips or spots of adhesive. This is common with flexible single-ply roof membranes. Fasteners are typically placed in the seams area where it can be covered by the overlapping sheet. For loose laid systems, the membrane is unattached to the substrate and is held in place by ballast. Restraint is required only at perimeters and curbs. Loose laid roofs are used with elastomeric EPDM systems and some thermoplastic TPO systems. These are very inexpensive roof systems if the structure can handle the ballast weight. A word of caution: in positive pressure buildings, air barriers should be used with loose laid and partially attached membranes to avoid billowing and peeling. With regard to labor costs, the labor costs are highly intensive with the BUR and MB systems, moderately intensive with the structural standing seam metal roof systems. The system is very unforgiving of installation defects, however. Medium intensity systems, fully adhered and mechanically fastened single ply, and low intensity from the standpoint of labor are spray foam, which requires the smallest crew but is the most machine intensive and weather sensitive. Table 12 indicates some typical slope limitations for low slope roof systems. The systems covered are ballast membranes, gravel surface built-up roofing, cap sheets with narrow lap widths, and MB smooth or cap sheet. With regard to principal considerations when specifying steep slope, water shedding roofing, this category covers systems that range from asphalt shingles, wood shingles and shakes, clay and concrete tiles, slate and metal lookalikes. Also included are architectural metal panels with a variety of seams, referred to Figure 11. Slopes are generally 25%, 3/12 or greater. Most must be continuously supported on a solid deck, for example plywood or oriented strand board, OSB. However, some varieties, clay and concrete tiles, may be supported on spaced horizontal batten boards. Underlayments such as roofing felt, self-adhering MB, or plastic film are usually required over the entire roof to provide a secondary line of defense against driving rain and blowing snow. In cold regions, a completely sealed MB underlayment is needed along eaves, in valleys, and at dormers, skylights, chimneys, and such to resist leaks from water ponded behind ice dams. Figure 11 indicates typical architectural metal seams. Flat, batten, and standing are illustrated. With regard to aesthetics, by their very nature, steep roofing is highly visible. Appearance may be of primary concern to the designer. Regional preferences exist. For example, red tile roofing is very common and highly desirable in the Southwest, while light gray concrete tile is preferred in Florida. Wood shakes give a textured, natural look preferred in the Pacific Northwest. Labor intensity and labor skill. High intensities are heavy brittle units of clay, tile, or slate. Medium intensity of labor, architectural metal, and wood shakes, and then low intensity is shingles. With regard to water shedding, steep roofs rely on gravity to cause water to flow away from headlamps. Recommended minimum slopes are shown in Table 13. Lower slopes are sometimes permissible by increasing overlap or enhancing the waterproofness of the underlayment. Table 13 indicates minimum slopes for typical steep slope roofing systems. Valleys must be well constructed. The slope of a valley will be less than that of the intersecting planes that form it. Exterior drainage over the roof edge or to a gutter is typical, but may be troublesome in cold regions since ice dams may form there. Sealed underlayments of self-adhering modified bitumen are typically used along the eaves to at least 24 inches beyond the interior wall line, refer to Figure 12A, and as valley lining. Occasionally, the entire roof deck is covered with such a membrane. Note that this can lead to problems if indoor moisture is not isolated from the roof by well-made vapor and air barriers. Underlayments are used in steep roofing as a secondary defense against water penetration. Refer to Figure 12B. These include number 15 felt, number 30 felt, and self-adhering MB sheets. For hydrokinetic and crafted metal, self-adhering MB sheets are essential as a secondary water barrier. Figure 12A indicates self-adhesive eaves flashing. Underlayment is sealed from the eave to 24 inches within the wall line. Figure 12B indicates underlayment for steep roofing where the underlay felt is unsealed. Steep roofs generally cover an attic space, refer to Figure 213, with the exception of cathedral ceilings. The floor of an attic can be inexpensively insulated with non-structural insulations such as fiberglass bats, mineral wool, and expanded vermiculite or treated cellulose. Where the thickness of the insulation is not limited by clearance problems, very high thermal resistances, i.e. R30, can be achieved. If a vapor retarder is required for a cold Arctic climate, the retarder needs to be placed on the interior warm side of the insulation. The attic space above this insulation should be ventilated to remove moisture and to keep the attic relatively cold. This minimizes ice damming at eaves. Figure 13 indicates schematically vented attic space. Table 14 indicates mean durability of common steep roofing. Maximum wind speeds associated with locality and storm type determine the needed wind resistance. ANSI, ASCE 795, and others provide design information. Air impermeable roof decks such as poured concrete with adhered or mechanically fastened insulation and fully adhered membranes are highly wind resistant. Tests conducted by the Factory Mutual system have determined that BUR systems installed this way have resisted 180 PSF. Metal panels are generally rated by the underwriter's 580 procedure with UL 90 ratings considered excellent. However, because some SSS-MR panel systems with UL 90 ratings have failed in service, structural standing seam metal roof systems must pass the ASTM E1592 test method. Ballasted single-ply systems rely on heavier and larger ballast in more wind-prone exposures. SPRI has developed wind guidelines in their ANSI SPRI RP4 document based upon ANSI ASCE 795 guidelines. Higher parapets have a beneficial effect on ballasted systems. Above certain building heights, SPRI recommends against the use of ballast. Mechanically fastened single-ply systems use narrower starter sheets and increased fastener density in high wind areas. Examples of layout can be found in Factory Mutual Loss Prevention Data Sheet 129. Sprayed-in-place polyurethane foam SPF systems have proven very wind resistant and are effective in protecting the structure against wind-hurled missiles. Roofs adjacent to airport tarmac activities should avoid aggregate surfacing, as loose aggregate may be blown off the roofs and sucked into engines. Loose stone ballast, which is much larger, is used successfully at many airports. Underwriters Laboratories lists wind-rated systems in their roofing materials and systems directory as class 30, 60, or 90. Factory Mutual Research Corporation lists wind-rated systems in their approval guide with ratings ranging from 60 to 210 pounds per square foot. For most steep roofing systems, additional fastening is required for high wind areas, that is 6 fasteners per asphalt shingle instead of 4, addition of nose clips for tiles, etc. The formation of ice can cause the roof membrane to split. Ice can also affect roofing performance by scrubbing the membrane and eroding the surface. This can be especially detrimental to materials with a relatively high glass transition temperature. Bituminous materials have a TG of approximately 32 degrees Fahrenheit. Modified bituminous materials with an SBS modifier can have a TG as low as minus 30 degrees Fahrenheit. EPDM membranes report a TG less than minus 40 degrees Fahrenheit. The TG of thermoplastics may increase with age, that is, loss of plasticizer in PVC. Ponding promotes ice damage, drainage avoids it. Falling ice, such as from overhead towers, causes impact damage. Ballasted EPDM provides some protection. Protected membrane roofs in which polystyrene insulation and ballast are placed over the finished roof membrane provide excellent impact resistance. Ice formation at eaves, scuppers, and gutters is a major design concern. For low-slope roofing, selection of internal drainage where building heat keeps the drain lines unfrozen is recommended. For metal and steep roofing, heating cables are sometimes necessary but not especially reliable. In cold regions, use of a cold roof in which the roof is ventilated to prevent formation of icicles and ice dams is preferred. Self-adhering waterproof membranes are needed to avoid leaks with ice damming. See Figure 10. Weather maps are available that generally divide the U.S. into regions that require resistance to severe hail, generally 2-inch diameter, moderate hail, 1.5-inch diameter, and areas of low hail probability. Hail resistance is affected by the compressive strength of the substrate, thickness of the membrane, tensile strength, and age and brittleness of the material. Snow removal operations in which shovels or snow blowers are used can cause severe damage, especially to cold, brittle membranes. Smooth, single-ply membranes in metal roofing are extremely slippery when wet or when a thin ice film covers meltwater. Roof walkways consisting of compatible materials are essential when it is necessary to walk on wet or frozen roofs. TI 809-52 recommends that SSS-MR should have a minimum slope of 8.3% in cold regions. Snow load information is available in ANSI ASCE 795, TI 809-01, and TI 809-52. Drainage is essential on all roofing systems. For hydrokinetic roofing, the drainage must be positive and rapid. Shingles, tiles, and the like generally have industry minimum recommended slopes of 33 to 42%. Sometimes a lower slope option is available if waterproof underlayments are used. Minimum slope for metal roofs vary from 4 to 33% depending upon the roof type. Low slope membrane should also comply with minimum slope of 2%, quarter inch per foot. Where ponding is unavoidable, such as in spray ponds, a BUR with double poured aggregate and bitumen is sometimes used. Coal tar pitch membranes are used at slopes as low as dead level and to a maximum slope of 2%, quarter inch per foot. Drainage is also needed. However, small puddles are inevitable as SPF is never completely smooth. Small puddles should dry out within 24 to 48 hours after inclement weather. Additional elastomeric coating is recommended where ponding is anticipated. For sprayed in place polyurethane foam, SPF, systems, positive drainage is also needed. However, small puddles are inevitable as SPF is never completely smooth. Small puddles should dry out within 24 to 48 hours after inclement weather. Additional elastomeric coating is recommended where ponding is anticipated. In re-roofing and recovering applications, correcting the slope to 2%, quarter inch per foot, is sometimes unfeasible because of low windows, flashings, etc. In these cases, tapered insulation at 1.5%, 3/16 inch per foot slope may be an acceptable compromise. Conversion of a poorly draining roof to a steep roofing system may be accomplished on a relatively narrow roof system built by installing new slope joists. Moisture can be carried through materials by diffusion or by the movement of air. Air barriers are needed to reduce air movement. They can be located anywhere within the building envelope. Vapor retarders, when needed, must be placed within the warm portion of the thermal insulation. In cold weather, warm, moist indoor air driven from within the building towards the colder exterior may accumulate during the winter, then dry back out again during the summer months. Guidelines for the use of vapor retarders in roofs are presented in CRREL Miscellaneous Paper 2489, Vapor Retarders for Membrane Roofing Systems. Figure 14A indicates suggested maximum allowable relative humidities where summer dryout should be adequate. Figure 14B is used to adjust Figure 14A for temperatures other than 60 degrees Fahrenheit. For hot, humid climates, a reverse vapor drive may occur, especially in cooler and freezer buildings. In this case, the membrane and wall retarders sealed and continuous. Roof vents and breathing edge details must be avoided. For freezer buildings, consider separating the roof system from the freezer. For buildings with high interior relative humidity, such as bakeries, laundries, pools, kitchens, dining halls with serving lines and the like, vapor retarders are considered essential. Figure 14A indicates interior relative humidities with interior temperatures of 68 degrees Fahrenheit in the continental United States and Alaska. Figure 14B provides temperature conversion factors when temperatures differ from 68 degrees Fahrenheit. Table 15 indicates typical indoor relative humidity in winter for types of buildings. Bituminous retarders are installed over solid fire barrier substrates such as concrete, gypsum board, or a fire-resistant insulation. Bituminous retarders have near zero perm ratings. For most membrane roofing systems, vapor retarder permeance shall be below 0.5 perms. Perm ratings for various vapor retarder materials can be found in the ASHRAE Handbook of Fundamentals as well as in industry literature. Non-bituminous single-ply systems may use plastic films as vapor retarders. These can be successful if the seams and penetrations are carefully sealed with tape. Puncturing the retarder, either accidentally or by installing mechanical fasteners, lessens its resistance to moisture. Protected membrane roofing systems, PMRs, are very effective against vapor drive from within the building. The roof membrane itself serves as the vapor retarder, as most, if not all, of the thermal insulation is located above it. Self-drying of the insulation, extruded polystyrene, to the atmosphere maintains the thermal resistance. SPF systems are commonly installed on recover installations where the old bituminous membrane can be sealed to form a retarder. Dew point calculations are necessary to ensure the dew point is within the upper SPF layer. In steep roofing systems, the retarder is usually a plastic film, treated craft paper, or foil facing on batt insulation installed with the retarder facing the interior. When an attic or cathedral ceiling is present, ventilation of the space above the insulation is essential since retarders are rarely completely sealed and some moisture accumulation would otherwise occur. Most codes recommend at least 1 to 150 net free ventilation area total at eave and ridge. When a retarder is not installed, to 1 to 300 when a retarder is in place. In cathedral ceiling construction, larger net-free areas are needed since friction losses in the narrow airway reduce ventilation. In structural metal systems where draped batt insulation is used, it's difficult to completely seal the retarder facer even if tape is used. When high interior vapor conditions exist, the use of a subdeck to support a retarder film may be necessary. Other roofing systems should also be considered as such systems are not good at resisting high internal relative humidities. Thermal insulation is important in modern buildings both for energy conservation and human comfort and may impact the roof membrane performance. Resistance to heat flow through the entire roof structure, which is characterized by the R factor, should be as high as possible, as is both practicable and cost effective, and in general the R factor should exceed 20. The U factor, which is the reciprocal of the R factor, should be 0.05 or less. Table 16 indicates the unit resistances, the resistivity of common roof insulations. Thermal insulation may be installed in 4 locations. First, underdeck insulation illustrated in Figure 15. Wood frame structures with steep roofing often utilize batt insulation placed between the rafters. Vapor retarders of foil, craft, or plastic film are located on the inside face of the insulation. With structural standing seam metal system, batts are draped over the purlins. In attics, the insulation is usually positioned between ceiling joists. An advantage of underdeck insulation is that inexpensive non-structural insulations such as batts may be used. Figure 215 indicates a typical underdeck insulation installation. A disadvantage is that roof deck suffers greater thermal stress than when it is overlaid with insulation. Another disadvantage is that it's difficult to vapor seal such construction and make it resist air exfiltration, and as a result moisture problems are prone to occur. Ventilation is usually required, but ventilating low-slope framed roofs lacking tight air barriers is apt to increase moisture problems, not eliminate them. Common underdeck materials include compressible batts of glass fiber and mineral wool. Thermal spacers of rigid plastic foam are placed over the purlins of SSS-MR systems to maintain the thermal resistance when the batts are compressed. For self-insulating roof decks, refer to Figure 16. And Figure 16 indicates a typical self-insulating roof deck system. Insulating decks such as structural wood fiber are less popular today because it is difficult to achieve high R values within the deck itself. In re-roofing situations, supplemental insulation would often be added on top of such a deck. In some new assemblies, a composite of structural wood fiber topped with plastic foam is used. The underside of these self-insulating decks can be exposed to the interior and serves as an attractive acoustical ceiling. With regard to thermal insulation within the roofing sandwich, refer to Figure 9. Insulation on top of the roof deck is the most common configuration for membrane roofing. For adhering membrane systems, the thermal insulation restrains the membrane against wind loss or shrinkage and must have adequate structural strength. For mechanically anchored and ballasted systems, compressive strength and stability are important. If hot asphalt or solvents are used in construction of the membrane, the insulation must resist degradation by these agents. Common materials for adhered systems include faced polyisocyanurate foam, perlite, rigid glass fiber boards, wood fiber, and cellular glass. Verify that the combination of membrane and roof insulation / facer are fire and wind rated. For mechanically fastened and ballasted systems, expanded and extruded polystyrene are added to the above list. They could melt or dissolve if placed in contact with hot bitumen or solvent-based adhesives. Some decay of R value is observed with HCFC blown foams, polyurethanes, and isoboards, due to diffusion of air and moisture into the cells of the foam. Manufacturers publish aged R values to reflect this decay. Always used aged R values for these materials. Since diffusion starts at the surface of the foam, thicker foams are more thermally stable. Wood fiber boards should be manufactured to use as roof insulation, meeting ASTM C208, not sheathing boards, and should be limited to 4 foot in length and width. When mechanical fasteners are used to secure thermal insulation, it is recommended that the nail one, mop one technique be used. This minimizes a thermal bridging and avoids nail popping of the membrane. When multiple layers of insulation are used, vertical joints should be offset to reduce heat losses. Straight through joints can take away 10% of a roof's insulating ability. With regard to protected membrane systems, in PMR systems, only extruded polystyrene is suitable in the sometimes wet environment above the completed roof membrane. This insulation protects the membrane from thermal stress and abuse. Ballast and filter fabric is needed to hold the loose-laid insulation in place. Figure 17 indicates a protected roof membrane system. The ratio of roof area on a low-rise commercial building is highly relative to wall area. Such roofs can provide a great opportunity for energy conservation. This can be accomplished by using well-insulated high thermal mass structures to reduce summer cooling loads, garden roofs, or high albedo roof coatings. For roofs in hot or temperate climates, light-colored roof surfaces reduce heat gain. For membrane roof systems, light-colored aggregate, gravel-surfaced roofs, or mineral granules and MB cap sheets reduce heat maximum surface temperatures by up to 35 degrees Fahrenheit over black membranes. Aluminum coatings are approximately the same, while white coatings have been observed to reduce temperatures by more than 45 degrees, provided that the roof stays clean. The use of pavers and heavy ballast reduce heat gain through thermal lag, that is, the high heat capacity stores some of the gained heat, delaying the startup of the building's air conditioning system. The ASHRAE Handbook of Fundamentals uses the term equivalent temperature difference in energy calculations. The smaller the ETD, the better the system is at reducing peak solar loads. Table 217 indicates equivalent temperature differences for different construction systems. With regard to fire considerations, topside fire ratings, because of its large surface area, roofing plays an important role in fire protection. Fire hazards can be defined as external, where the source is outside the building, such as from wind-blown flaming debris. Tests for external fire resistance are referred to in building codes as Class A, B, and C. An external fire rating is established by constructing and testing roofing assemblies by methods described in ASTM E108, also known as UL 790. In this method, relative degrees of fire resistance are established. Class A roof coverings are effective against severe fire exposures. Under such exposures, roof coverings of this class are not readily flammable and do not carry or communicate fire. They afford a fairly high degree of fire protection to the roof deck, do not slip from position, possess no flying brand hazard, and do not require frequent repairs in order to maintain their fire resistant properties. Class B roof coverings are effective against moderate fire exposures. Under such exposures, roof coverings of this class are not readily flammable and do not readily carry or communicate fire. They afford a moderate degree of fire protection to the roof deck, do not slip from position, possess no flying brand hazard, but may require infrequent repairs in order to maintain their fire resistant properties. Class C roof coverings are effective against light fire exposures. Under such exposure, roof coverings of this class are not readily flammable and do not readily carry or communicate fire. They afford some degree of fire protection to the roof deck and do not slip from position. They possess no flying brand hazard, and they may require occasional repairs or renewals in order to maintain their fire resistant properties. Class A, note, does not mean grade A. In this classification, only fire performance is considered. A specifier should select the degree of fire resistance required, but recognize that selecting a higher rating does not assure better waterproofing nor longer life. In fact, some compromise in durability may have been made to meet the higher fire rating. ASTM E108 fire tests may be conducted on steep roofing, membrane roofing, SPF, and metal panels. Listings of systems that meet these requirements are found in the Underwriters Laboratories Roofing Materials and Systems Directory and the Factory Mutual Approval Guide, and reports and directories published by several other qualified testing agencies. Qualified listings: if a roofing assembly fails to meet burn-through requirements of ASTM E108, it may still be listed for use with non-combustible decks such as steel, concrete, and gypsum. Roofing assemblies are listed at the maximum incline to which the rating applies, as long as the structure under consideration is at a lower or equal incline to that listed. It complies with the fire rating. If a listing is intended for use as a roof superimposed over an existing roof, it shall be listed in the UL Roofing Materials and Systems Directory under the category Maintenance and Repair Systems. In the Factory Mutual Approval Guide, it will be listed as a recover. In general, only the materials listed qualify, and only when used in the manner described in the directories. Additional insulation, for example, may worsen the flame spread. An internal underdeck fire is when the flame spread is underneath the roof deck. Listings are referred to by the approval rating, usually Factory Mutual Class 1 or Underwriters Laboratories Insulated Metal Deck or Non-Metallic Decks Construction. As background information, in 1953, a large insulated steel roof deck building suffered an unexpected catastrophic fire loss due to an underdeck fire exposure. The roofing components above the deck contributed fuel to spread the fire. Tests conducted on full-scale test buildings confirmed the hazard. In the late 1950s, laboratory tests were established and correlated to the full-scale data. Factory Mutual uses a calorimeter to establish fire performance, while Underwriters Laboratories uses a modified Steiner tunnel test. Successful systems are listed by Factory Mutual as Class 1, while Underwriters lists them as either rated metal deck or rated non-metallic assemblies. The underdeck ratings do not assure zero risk. The ratings assume an acceptable risk, assuming normal fire detection and fire control procedures are available. If an insulated steel deck system fails to comply with the requirements of Factory Mutual Class 1, it is designated Class 2. Class 2 constructions may be converted to Class 1 by the addition of underdeck fireproofing. Class 2 constructions may also be acceptable if an approved sprinkler system is used. Fire endurance tests. These are time temperature tests per ASTM E119 in which the roof ceiling assembly is subjected to a rising heat load until either the interior structural elements yield or the temperature on the exterior roof system reaches 250 degrees Fahrenheit above the ambient. The minimum elapsed time required before the endpoint is reached is usually established by building code or occupancy, i.e. 1 hour, 1.5 hours, etc. Rated assemblies are listed by Underwriters Laboratories in their fire resistance directory and by Factory Mutual in their approval guide. Other testing agencies list rated assemblies in their directories as well. Assure that fire compliance ratings pertain to the entire assembly. Each component of the system must be listed in the above directories. Materials delivered to the job site should bear labels indicating compliance with the construction intended. The label also provides third-party assurance that the products delivered to the construction site are essentially unchanged from those tested and listed. While membrane roofing materials in general do not affect seismic stability of a structure, components of the roof system may be important. Roof decks, for example, usually serve as a diaphragm, increasing lateral stability. Structural metal systems with floating clips require bracing, since the structural standing seam metal panels do not provide diaphragm action. An alternative to bracing is to use a steel subdeck to serve as the shear diaphragm. Heavy roofing materials such as ballast or pavers may result in an inertia effect that should be included in the design. This may be beneficial or detrimental. In steep roofing, seismic motion may shatter materials such as cement and clay tile. Correct use of mechanical anchors may prevent damage. Twisted wire systems are recommended for earthquake zones. The National Tile Roofing Manufacturers Association requires 2 nails or a nail and a clip on every tile to resist seismic damage. Restraining of roof tiles. A Title 24 California code addresses the attachment of tiles and allows the combination of wire tie and nose clips, wind locks, or tile locks. Nails or wire ties are to be copper, brass, or stainless steel, 11 gauge minimum with 2 per tile. Nails are to penetrate roof sheathing, battens, or support members, 3/4 inch minimum. Ring shank nails may be used when sheathing thickness is less than 3/4 inch. Parapet walls must be used with care. Through wall flashings or cut reglets must be avoided as they reduce the wall's resistance to lateral forces. Seismic straps, heavy metal plates, are sometimes installed over plywood roof decks and between decks and walls. Where roof insulation is not used, i.e. a West Coast cap sheet construction, use construction details provided by the Western States Roofing Contractors Association on how to roof over straps, indicated in Figure 18. Figure 18 indicates roofing over the thick seismic straps. Complete sectional views of every location where the roof changes plane or where there is a roof penetration or attachment should be provided on contract drawings. Sections and design details should be drawn to a legible scale with each element of the roofing system identified. And that brings us to the conclusion of this brief discussion of roofing systems. I hope this was about what you were looking for, and that this will give you a little bit of technical guidance that you can use on projects as they come across your desk in the future. And with that, let me thank you again and have a nice rest of the day. Thanks a lot. Bye.